Are we ready?
Just a minute. Yes. Yes, I'm ready.
Perfect. Our next speaker is Matilde Lalin from University de Montreal. She will tell us about sums of certain arithmetic functions over f sub q of t and symplectic distributions. Please, you have the floor. Thank you.
Thank you. Thank you, Florian, for the presentation. Thank you, Florian and Claude, for the invitation to speak. I'm very happy to speak, although I shouldn't say I'm happy to be here because I'd rather be in Argentina giving this talk. What I'm going to talk about is joint work with Vivian Cooperberg from Stanford University. And I'm going to be talking about some properties of some arithmetic functions. So the first arithmetic function that I'm going to be considering is the k-divisor function. So I say a couple of things over number fields as an introduction, but then I'll be talking about function fields for the rest of the talk. So the k-divisor function is defined as a number of ways we can write positive integer n as product of factors that are also positive integers. And this is an order product. We are going to fix k factors. So this is what the k of n is. And another way of thinking about it, which is going to be important for us, is that it's coming out of the coefficients of the k power of the Riemann zeta function. And the natural question to ask is to study the sum of the kn when n is less or equal than some x. And if we do that, say with Perron formula, we're going to get some estimate that given by a polynomial of degree k minus 1 in log of x times x, some error term delta k of x. And so that would be main term and error term. But then if we want to study this distribution further, we want to consider, for example, the variance. And so a question about the variance would be to estimate the value, say, of this integral. And well, there are some, this is known for k equals 2 and for k greater than or equal to 3 under Riemann hypothesis. Now, in this talk, we are concerned about two more specific types of problems. So the first one has to do with short intervals. So instead of considering decay of n up to x, we're going to consider with the n moving in some interval x and x plus h. And so typically here, the hard part is when h is small respect to x. And the other question is with arithmetic progression. So we are still doing the sum on n less or equal than x, but we are restricting to some congruence mod q. And these problems were studied by Keating, Rogers, Roddy Gershon, and Rudnick in the context of function fields, okay, so over FQT, and what the results they obtained allow them to make conjectures over the number field cases and recover some results of Lister for the first problem and Lau and Shao for the second problem and other people. So like I said, now I'm going to start talking about function fields. So for us, we are going to be working with FQT. So Q is a power of a prime and it will be odd when in DAB is odd. So we have the FQ is a finite field with Q elements. And so our field itself is going to be the rational functions in T with the coefficients in FQ. And obviously there is the ring associated to it, the polynomial ring. And it's important to keep in mind, so there's this, all this arithmetic structure over the polynomials over FQT. And so an equivalence to what the primes, the positive primes are in the integers, is the monic irreducible polynomials. We can also talk about norms. So if we have a polynomial f an fqt, the norm is going to be given by q to the degree of f. And we can also build zeta function and even also L functions. This is going to be relevant later. Okay, so for the zeta function, we're going to do the sum over all the f polynomials that are monic, okay, of 1 over the norm of f to the s. And what happens in this psi, the psi of function fields, is that the Riemann hypothesis is true, is known to be true. And this is, it goes beyond what I'm saying about just the Riemann zeta function. Okay, this is going to be true also for the L function, and this is going to be relevant in this talk. Now, now going back to the divisor function over function fields, the way we're going to define this is for, again, a monic polynomial. We're going to be writing f as a product of k monic polynomials. So the same that we had before, but now product of monic polynomials as opposed to positive numbers. And again, this is going to come up as the coefficient of considering the zeta function to the power of k. Now, for the results I want to talk about in the next slide, I need to define some objects. They are called the secular coefficients. So if we have a matrix, an n by n matrix, the secular coefficients are going to be just the coefficients of the characteristic polynomial, I mean, given in this version. So these are symmetric polynomials in the eigenvalues. Now, first, I want to go a little bit in more detail about what Keating, Rogers, Rodity Gershon, and Rudnick did. Okay, so they consider, like I said, the question of the divisor function over function fields in the two versions, the two questions that I mentioned at the beginning. So the first question it was about short intervals. Okay, so what is the equivalent of short interval here? So we're going to go over f monic and then f close to certain fixed monic polynomial in the sense that the norm is bounded by certain constant. And what they found was that they studied the mean and the variance. So what is interesting is really the interesting computation is with the variance. And they found that the variance as q goes to infinity is asymptotically like certain integral. And so this is an integral over the unitary matrices. And what we are integrating is a absolute value square of certain sum of secular coefficients, okay, where we have that the sum, okay, so the sum of the indexes is n, and I think I didn't say what n was, but n is a degree. Yes, I said. So n is a degree of a, okay, and yeah, and well, basically moving up to certain value. Now, so this is a result that they got for this problem. Now for the other problem, so this is moving over arithmetic progression. So again, we're going to consider the sum of decay f, but now f congruent to sum a modulo q. So q is a square-free polynomial. And what they got is, again, some limiting integral as q goes to infinity, expressing the variance of this sum. Okay, so the integral itself is very similar. Okay, so there are some adjustments with the different indexes. Okay, so again here n is the degree of f. Okay, and there is also the degree of q coming into play. Now, they Keating, Rogers, Roddy, Gershon, and Rudnick went on and studied what this type of integral give. Okay, and they found, for example, and so if we now write this in terms of small n and big N, okay, so before this big N was dependent on the problem, okay, but they study, for example, the asymptotic, okay, so they express this integral as some like an asymptotic respect to n, so it's going to be n to the k squared minus 1 times some coefficient plus smaller error terms, and then this coefficient is actually a polynomial in small n over n, and they prove that it's actually piecewise continuous polynomial function. And they went on and studied these and many of the properties of this. So the question we started with was, what about symplectic distributions? So let me give you a bit of context here. So both Cooper and I are part of a group and at the American Institute of Mathematics, where we are discussing these gamma KCs, the symplectic version, in different points of view. So we went on saying, okay, so let's see if we can find problems that are similar to the problems that we are discussing now, but that need a symplectic distribution when we take the limit, as opposed to the unitary ensemble. And so the first problem that we consider is, obviously it's not going to be the same, exactly the same problems, okay, but they are kind of similar. So the first problem we consider takes the sum of dkf over a monic polynomial of degree n that are a quadratic residue when viewed as modulo p, where p is a monic irreducible polynomial of fixed degree. So we consider this problem, and for this problem, we get as q goes to infinity that the variance, and here I'm being a little bit careless about when I say the variance, but I'm going to discuss what I mean by the variance later. But the variance approaches essentially an integral of the secular coefficients with the same kind of formula, okay, the sum of the secular coefficients with a fixed sum for the indexes to the square, okay, but now over the symplectic matrices. We also consider a different problem. So remember the initial problems, okay, let me go back a minute. Okay, so the initial problems that I mentioned were short intervals and arithmetic progressions. So I like to think about this problem as a version of arithmetic progression. I mean, it's not really, but we are congruent to a quadratic residue. And we also have a version of short intervals, okay? And the version of short intervals in this context has to do with taking the f, as opposed to be in a short interval, it is in a short interval in a sector of a unit circle, okay? So the idea goes that you can define an analog of Gaussian numbers over function fields, and then talk about what it means to have a unit circle. And then what we are going to do is do the sum over some sector of this unit circle. So I have a bit more detail here, just in case people want to see it more, but basically the unit circle, we are going to think in terms of formal power series on FQ adjoint square root of minus t. So this is the I that we get. And so the unit circle is the elements that have norm 1, okay? And we can talk about angles in the obvious way, I mean, in the analogous way. And so that's what it means to fall into a sector, okay? To have the argument falling into certain part of the unit circle. Okay, and with this, we also have a very similar result, okay, expressing the variance in the Q infinity limits as an integral of symplectic matrices, again, with our friend, the sum of the Securia coefficients. Let me mention that we also look at the von Mangold convolutions. Okay, so the von Mangold function that comes, well, given by log of p if we have a power of a prime p and 0 otherwise, and shows up as coefficients of minus zeta prime over zeta. And we can extend this to monic polynomials in the obvious way. And then by convolution, I mean this. So I mean doing, well, exactly the convolution of the von Mangold function, a k-fold convolution. It's important to keep this in mind because there are several versions in the literature that are slightly different, depending on different needs that people have. So in this direction, we actually study all these problems. So the first two are with unitary matrices, so they are basically the analog problems that the ones I described from Keating and his co-authors. And then we also study the symplectic versions that I mentioned with the divisor function, but now with the von Mangold convolution. And so I wondered, how much time do I have? I don't know anymore.
We are running about 10 minutes behind, so you can take another 5-6 minutes if you want, okay, and leave a couple of minutes for questions.
Okay, thank you. Okay, so I just wanted to give a little bit of an idea of how the proof goes for one of them, because all of them have a different story a little bit. But say if we consider the von Mangold convolutions with quadratic residues mod p, then what the statement says is that the variance is going to be given in the limit as some integral over the symplectic matrices, but now instead of having Securia coefficients, I have traces. Okay, and so how does it work? Okay, so when I'm going to talk a little bit more in general about quadratic characters in function fields. So if I take D, square-free monic polynomial of degree 2g plus 1, we can define the quadratic character mod D. It's going to be an odd character, and what it means by odd is that is non-trivial over the constants. Okay, and then the L function is going to, we can write it, well, here's the definition of the L function, but then we can express it in terms of some characteristic polynomial of the Frobenius class, which you can think of a conjugacy class of some unitary matrix. The fact that the character is odd means that we just get the determinant and there are no extra factor, and then we can use the generating this to get a generating series involving the von Mangold convolution. And then with that, we have a very nice expression of this sum. So the sum of the von Mangold convolution multiplied by the character. And the nice expression is in terms of these sums of the traces. So this looks a lot like the thing that goes inside the integral. Now, there is a question here. So the statement I gave you is with P, an irreducible polynomial. And here I'm saying that I have a general story with a square free. The problem is that if I keep a square free, then it's a little bit hard to manage what happens with the error term. So we are going to restrict to P monic irreducible. And so look, what I said is still true, okay? And we can write the sum that I want to consider, we can write it as a term, as a main term, over delta, but now there is no restriction on quadratic residues. And then this error term coming from the expression I told you before. So the main term we have size q to the n, but the error term has size q to the n over 2. And this is the Riemann hypothesis in plane. And then the variance, we can just replace very easily by this expression. And here I said that I was lying a bit about what the variance is. So I'm really taking this term. So this term approaches the mean, but it has other components to it. But anyway, so when we write what this expression is, it gives this m from before. And so if you look at what the formula we have, we end up with a sum of traces to the square. Okay, now the last ingredient that we need is the ability to take the limit when q goes to infinity. And this comes from equidistribution. Now, we know very well that if we take the hyperelliptic ensemble, meaning these quadratic characters, modulo d, square free, monic polynomials, etc., then we have equidistribution in terms of the symplectic ensemble of matrices. However, this is not what we have, because like I said, to make life easier before, instead of working with square free polynomials, we restricted to irreducible. And so what we want now is actually to understand what happens to equidistribution if we only take irreducible primes of degree 2g plus 1. And so actually, we were wondering about this, and we ended up talking to Katz about this. And he came up with this very, very beautiful idea that actually you can prove that the monodromy of not just h to g plus 1, so not just the whole square free polynomials of fixed odd degree is a symplectic group, but also if you prescribe certain factorization inside them. So if you only consider the polynomials, the square free polynomials that are forced to be factorized in a certain way, it doesn't have to be irreducible factors, but it's just you force the polynomial to say have a factor of degree 2 and a factor of degree 2g minus 1. And so with that, so he was able to prove that the monodromy of that is still the symplectic group. And then with that, one can do inclusion-exclusion to go about, to prove the same for polynomials that have a very specific fixed factorization type. So the difference between this family HD1Dn and PD1Dn is that with PD1Dn, I'm going to ask that the factors be irreducible, okay? And so that includes, in particular, the case where I have just one irreducible factor of degree 2g plus 1. So just irreducible polynomials. Okay, so with that, we get the distribution, and then we can take the limit and prove this theorem. And so let me just, okay, so that's the theorem. And so let me just say a few words about what can we say about the integral. So random matrix theory has a lot to say about this other integral. So this other integral, so the one that we have in our theorem, okay, is the square. Is the square of the sum of traces. So random matrix theory, there are lots of results from different points of view, working with just the sum without the square. And this, in our case, has to do with the discrepancy. And here, luckily, because we didn't do the variance with the actual mean, the discrepancy is something interesting. And so we can say that, but if we want to study the variance, we need to have a square inside the integral. And so for now, we only know the very simplest cases. So the integral of just the trace of one, so one trace to the square is known, and we can also we can also compute the integral of just one security coefficient square. And so with that, we can find what the gamma should be in our case. So I'm going back to this main coefficients of the asymptotic that was originally described for the unitary case. So in this case, we can describe the asymptotic for the symplectic case, but obviously there is much more to be studied. And so that's the final question. What can we say? We would like to have formulas in the random matrix theory with the square. Thank you very much. Muchas gracias.
Thank you very much, Matilde.